Good morning. This is Dr. KJ Berry. My presentation today is a study aid in the area of fluid mechanics with a focus on Bernoulli and manometry. And I will be talking about a logical and structured mental process that one should follow to solve many problems in fluid mechanics. So, first of all, let's look at this first problem. It's a involving airflow. Airflow is steady and frictionless, as shown, and we have flow in a converging, diverging nozzle. And and if the flow is large enough, the pressure in the constriction here will be low enough to draw water into the tube. Of course, with Bernoulli, we know that pressure and velocity are inversely proportional to each other at the same elevation. So the air will flow from point 1 to point 2. Because we have a decrease in cross-sectional area, we will expect to have an increase in velocity but a decrease in pressure. That decrease in pressure will create a vacuum to draw water up into the tube, which is nothing more than a manometer. And a manometer, and this is just a large container of water. From point 2, we have an increase in area, which means that which means I would have a decrease in velocity and a decrease in velocity, which means a increase in pressure. Once again, we have a free jet. A free jet. The definition of a free jet means that the pressure of the fluid is exiting to the atmosphere, and that we have zero pressure at the exit. So it's important to have an understanding of the flow parameters and understand the definition of a free jet, understand what is the definition of a manometer and how does it work. So our problem is to determine the volume flow rate Q and also determine the inlet pressure requirements to create this deflection of zero point 0.3 meters in the tube of my manometer. So the first thing that we want to do is to be able to ask ourselves, what are the fundamentals? We never try and solve a problem without first saying, what are the fundamental guiding principles that will determine the roadmap to solve this problem? Point one, I know that I have fluid flowing in the duct. It's frictionless. It's steady state. So therefore, I know that Bernoulli is an important fundamental principle because I have frictionless fluid flow flowing in the duct. Because I have a change in diameter, I know that maybe mass conservation is important because I have a change in cross section between 1 to 2 to 3. Because I have a manometer here, I know that the application of hydrostatics should give me a pressure differential uh, uh, within my manometer. I also want to ensure that I uh, identify critical points in the problem. Never try to solve a problem involving a streamline, involving the application of Bernoulli's equation, without identifying points along that streamline. So I want to look at the inlet and exit points. Here we're talking about points 1 and point 3. A static pressure point 2. This is a static pressure point. It is located above the inlet to my manometer. We always want we always want to locate a computational point above the inlet to my manometer. We also look at to see if we have a stagnation pressure point. Here in this problem, there are no stagnation pressure points, and so we don't need to identify those points. We also, if we have a manometer in the problem, we want to identify a point at the interfaces between the different manometer fluids, including the exit point or the atmosphere. Here, there's only one fluid in my manometer. It is H2O, and the exit point is at point 4. It's the interface between the water and the atmosphere. So we want to identify those points because in the problem we may be solving for multiple streamlines involving multiple points. And we always want to make sure that we identify those points up front to help guide us along our solution path. So the next step in the process is if we have a uh, manometer, we really want to use the equations of hydrostatics first and apply manometry to first to identify the knowns and unknowns. And we want to be consistent. So here we're talking about applying hydrostatics between point 2 and point 4. Point 2 is above the inlet to my manometer, and point 4 is at the free surface of my container. And we ignore the air pressure changes above the inlet to my manometer. So we ignore the change in air pressure between point 2 here and the inlet to my manometer tube. The reason is because we have air, which is a very compressible substance, but it doesn't compress very well. It will not compress the water contained within my manometer tube. So so there will be very little changes in the air pressure between 2 and the inlet of my tube as compared to changes in pressure along the axis of the tube. So therefore we ignore the changes in air pressure above the manometer fluid. So applying hydrostatics between point 2 and point 4, we would get that point 2, the pressure 2 plus gamma delta Z is equal to the pressure at 4. Of course, gamma is the specific weight of the manometer fluid times the deflection or the elevation differences between point 2 or the inlet to the tube and point 4. So since pressure at 4 is open to the atmosphere, I know then that P2 is minus gamma sub m times the delta Z. And gamma of my manometer, the fluid in my manometer is water. The specific weight of water is 9,800 newtons per cubic meter times the elevation differences of zero point 0.3 meters. And the pressure at 2 is negative, as I expect it to be, negative 2.94 kPa. At this point, I also want to compute the ratio of P2 divided by gamma of air. I know that gamma of air is 12 newtons per cubic meter. So therefore, P2 divided by gamma of air is minus 2,940 pascals. And we note that we don't use kPa. We always want to use our base units of, of pascals and not kPa. So therefore, we have P2 over gamma of air is minus 245 meters. So step 3, we want to apply Bernoulli involving our static pressure tap, our static pressure point above the inlet to my manometer tube. So this is very important. It's important because I know something about that point. I know the pressure at that point. And so if I want to apply Bernoulli's now between 1 and that point or 2 and that point, then that point I know some information at that point. So I want to apply Bernoulli to the point associated with my manometer. I also want to combine that information with mass conservation because I have a change in diameter along a streamline that goes from 1 to 2 to 3. And with that information, then I want to determine the volume flow rate. So applying Bernoulli's between 2 and 3. I could have also applied Bernoulli's between 1 and 2. But I asked myself, do I know more information about point 1 or do I know more information about point 3? Well, I do not know the pressure at 1 or the velocity at 1, but I do know, and I don't know V3, but I do know the pressure at 3. So I do know, have some information regarding uh, uh, the I do have some information about what's happening at point 3. I know that the pressure 3 is 0 because it is a free jet. So therefore, and I know that Z2 is equal to Z3. So therefore, applying Bernoulli along a streamline between point 2 and point 3, I would have the P2 over gamma of air plus V2 squared over 2G is equal to P3 over gamma of air plus V3 squared over 2G. I know that P3 is 0 because it's equal to a free jet. And now I want to combine that with mass conservation because I have a change in my diameter between 2 and 3. So therefore, I know that A1V1 is equal to A2V2 is equal to A3V3. So between point 2 and point 3, I know that V2 A2 is equal to V3 A3. Or solving for V2, I know that then that V2 is equal to 4 times the velocity at 3. So I know that V2 will have a higher velocity. I know that that V2 is equal to 4 times the exit velocity V3. So now if I combine mass conservation and Bernoulli, so I want to plug in my expression for V2 in here into the value of V2 squared in my Bernoulli equation. So therefore, if I combine terms, I would have then that V3 squared over 2G times 16 minus 1 because I know that I know that V2 is 4 times the value of a V3. So V3 squared over 2G times 16 minus 1 is equal to minus P2 divided by gamma of air. Now, I recall that I know this value because P2 divided by gamma of air is an expression that we derived or we calculated from the application of the manometry equation involving point 2. So that's a reason why we use manometry first. That gives us some information about that static pressure point. So uh, so so now I can solve this expression for my velocity at point 3 is equal to the square root of minus P2 divided by gamma of air times 2G divided by 15. See, this 16 minus 1 is equal to 15. And I know P2 over gamma, and it had better be negative because I can't take the square root of a negative number. So 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 this tells me that my algebra is correct. So P2 over gamma of air had better be a negative number. And it is. P2 over gamma is negative 245 meters. So therefore, I can solve for my velocity at point 3 after combining Bernoulli's mass conservation and also combining with manometry. And so therefore V3 then is the square root of plus 245 times 2G divided by 15, which is plus 17.9 meters per second. And since I know my velocity, I can find my volume flow rate, which is A3V3. I know that the area is the area that is normal to the flow stream, or pi d squared over 4. So Q is equal to the area times my velocity. So my volume flow rate is 0.0351 cubic meters per second. So So now I can solve for my velocity 2 and my velocity 1 because I know Q. I know that Q for mass conservation is A1V1 equal to A2V2 is equal to A3V3 for steady state conditions. So this allows me the opportunity to solve for V2 being Q over A2 and V1 being Q over A1. I note that V1 is also 17.9 meters per second, which is identical to V3. And I will always have the same velocity in sections of ducts or pipes in which I have the same diameter. So that's how I know that my algebra is correct, my analysis is correct. I know that my velocities in sections of pipe in which I have a constant diameter should be the same. So now I want to find the pressure at one. I can use I can apply Bernoulli between point 1 and point 2. I can apply Bernoulli between point 1 and point 3. Depending upon if I use 2 or 3, it will just depend upon how much information I know about point 2 combined with or compared to what information I know about point 3. So I always want to look at the points first and to identify, well, which point I know more information about. In this scenario, in deciding if I should go with point 1 or point 2 or point 1 or point 3, I know the pressure and velocity at point 2, and I know the pressure and velocity at point 3. So either one I choose, I should get the same answer. So let's check it out. If I apply Bernoulli between point 1 and point 2 now, I would have P1 divided by gamma of air plus V1 squared over 2G is equal to P2 over gamma of air plus V2 squared over 2G. Solving for the pressure at 1 is equal to P2 divided by gamma of air. I know that value. That value is minus 245 plus V2 squared over 2G minus V1 squared over 2G. And I know those values from up here from when I apply mass conservation. So therefore, it turns out that I know V2, I know V1, and that the pressure at 1, wow, look at that. The pressure 1 is minus 245 plus 245 times gamma of air, and that's equal to 0. So the pressure at 1 is equal to 0 gauge pressure. Now, let's look at applying Bernoulli's between 1 and 3, just as a double check. Between 1 and 3, applying Bernoulli's, I would have P1 over gamma of air plus V1 squared over 2G is equal to P3 divided by gamma of air plus V3 squared over 2G. And since I've already said that I know that P3 is 0 gauge pressure, and I know that V3 is equal to V1. So once again, I see that P1 over gamma is equal to 0, as with my first example in which I looked at applying Bernoulli between 1 and 2. The purpose of this exercise, of this study aid, is to help you understand a logical, methodical approach to solving multiple problems that may involve mass conservation and Bernoulli, because it doesn't matter about the geometry. It doesn't matter if you have a converging, diverging duct. It doesn't matter if you have manometer. So involving problems in which you have in which you are trying to apply Bernoulli's, manometry, and mass conservation, there's normally a step-by-step process, a logical process that if you solve the problem in a logical, structured way each and every time, then mentally you will develop a problem, a structured problem solving approach that gives you a roadmap to solving many problems that you perhaps may not think you can solve when you first sit down to look at the problem statement. But but the process involves asking yourself what are the fundamental principles involved in solving of this problem, and and to understand the step-by-step process that one would go through to to make the solution easy and consistent from problem to problem. Thank you very much.